Thank you for the introduction. This is joint work with my colleagues from Maastricht University and Enigma Bridge. I will structure the talk according to our contributions. First, we recovered the structure of RSA primes as used by an asymmetric library of Infineon technologies. Then I will show how we applied Coppersmiths method on RSA keys of this specific format to develop a feasible factorization attack. Then I will speak about the impacted domains, which we surveyed thanks to the fingerprinting method developed by us. These include electronic identity documents, trusted platform modules, and authentication tokens, and other devices with FIPS 140 certification. In the end, I will introduce the proposed mitigations and summarize what lessons can be learned from this incident. The motivation for this research was our paper, The Million Key Question, published last year at Usenix Security. In this work, we generated millions of keys from different implementations of RSA key generation and compared their statistical properties. For example, it's plain to see from this figure that the distribution of the primes generated by software libraries such as Microsoft differs from one generated on a smart card made by Infineon. The data sets of this paper are online, so if you want to search for other vulnerabilities in other manufacturers, you can just download this and work with the keys. One of the most important properties and statistics of these RSA public keys was the distribution of keys modulo small primes. On the left, you can see that random primes are distributed almost uniformly, modulo small primes. However, Infineon keys were exhibiting some specific structure. This was the main motivation for us to look into this in more detail. Already in this paper, it was quite obvious that this structure was providing a strong fingerprint of these keys. First, to agree on the notation, the capital N is the public RSA modulus, which is the product of two private primes P and Q. Ideally, you generate a random number until you find a prime. However, this approach is not feasible on constrained devices such as smart cards, and that's why manufacturers introduce efficiency improvements. Such as in the case of these cards, all the primes are generated with the following structure: K times M plus 65,537 to the power of A modulo M. M is a known constant, and it's a product of small consecutive primes. This means that only the values of A and K are chosen randomly, and all the primes differ only in these two values. This structure has several consequences. The first one is the fingerprint, which is very reliable. We did not find any false negatives, and the false positive rate is completely negligible. The second consequence is that these primes generated in this way have fewer bits of entropy than randomly sampled primes, as you can see on the picture on the right. And finally, it's possible to develop a feasible factorization method on the moduli which have primes of this form. For our attack, we modify the Coppersmiths method. Here I will explain it as a black box tool. Given a partial knowledge of a private RSA key, the method is able to compute the full private key. In a typical scenario, the public modulus N is a known value. However, the factorization of this modulus, the private primes P and Q, are kept secret. If an attacker gains the access to a partial knowledge of one of the primes, the requirement here is at least half of the bits of the prime. In this illustration, the attacker knows the half of the least significant bits of P. Then she can take the known values of N and P low, put them into the Coppersmiths method, which in turn computes the full knowledge of the prime P. This, of course, means that now, by simple division, the attacker also has the prime Q and can compute the private exponent. We leverage this method and use it with the specific format of primes in question. To learn the value of this prime, we have to learn the values A and K. But thanks to Coppersmith's attack, we only need to find A, and then we are able to compute K from this. This means that the basic factorization algorithm will work as follows. We make the guess on the value of A and try to compute K using Coppersmith's method. For an incorrect guess, we try again, but for a correct one, we get the full value of P. After making the guess on the value of A, we can compute this value of 65,000 to the power of A modulo n, and these will be our known bits for the Coppersmiths method. And then we compute the value of K. If we look at an example of 1024-bit primes as used in 2K moduli, it may seem at first that this method is not feasible, since the size of A is quite large. However, keep in mind that Coppersmith method only requires about half of the known bits. This means we can make this value m smaller by finding a divisor m prime of this value m. It has to be a divisor to preserve the structure of the primes. In practice, this means that with the decreasing size of m, also the size of A associated with it decreases. So, for example, in the same case, we can factor 2 kilobit moduli if we try all the 35-bit values of A prime. It's important to note here also that the values of A prime can be guessed in parallel and independently. That means we can arbitrarily divide this region for the search of A prime between a large number of computers, so we can run the attack much faster in parallel. We performed this type of parameter optimization for all supported key lengths on our card. These range from 512 to 4096 bits in 32-bit increments and are displayed on the horizontal axis. On the vertical axis, which is in logarithmic scale, we can see the worst case factorization time in years. The average case for the factorization is half of the values, but of course, some keys can be factored much faster. If we begin with the keys of 512 bits, we can note that these can be factored in under 2 CPU hours. The attack complexity then quickly increases. However, for the 1 kilobit primes, for the 1 kilobit moduli, it drops again, meaning that they can be factored under 2 CPU months. This is equivalent to about $76 on Amazon Cloud. This drop happens again right before 2048-bit moduli, making them factorable on Amazon Clouds in 100 CPU years, which would cost about $40,000. However, if an attacker has access to their own infrastructure, we computed the energy price to be less than $1,000 to break this key. This drop happens again before 4096-bit moduli, And the reason for this is that the manufacturer chose 4 distinct values of M for their algorithm, which are increasing with the increasing size of the moduli. You may notice that there are certain gaps in this graph. Oh, sorry. Um, these gaps are caused by the fact that the size of M uh, can become smaller than required for Coppersmith attack, which means for certain key lengths, this is less than half of the bits of the modulus, of the prime, sorry. One such key length is 3936 bits, which is not practically factorable by our method because the conditions are not met. It's important to note here that the attack complexity does not strictly increase. So as illustrated by the 3 kilobit key, which is shorter than the 4 kilobit one, but it requires much more factorization effort to break. In our survey of real-world keys, we did not find this specific key length, and most people just stick to the common key lengths. This brings me to the impacts of our vulnerability. The flawed RSA key generation method was implemented for an asymmetric cryptographic library used in secure chips. So just this method and in the library is vulnerable. However, these chips are widely deployed. For example, they are used in trusted platform modules, or TPMs for short. You may have such module in your laptop, and typically it can protect sensitive encryption keys, such as for BitLocker, or in enterprise setting, it provides platform integrity. Microsoft has already released patches to mitigate this for BitLocker, and manufacturers of laptops are issuing the updates for the firmware. That means that the firmware of TPMs can be updated, and this library can be replaced. In the time before this mitigation started, we estimated the number of affected devices to be between 25 to 30% of all TPMs sold. This update is, however, not always possible, since in some cases, the library is written in read-only memory, which cannot be rewritten. This is a large issue for identity documents, such as EIDs and e-health cards. These were issued to citizens in Estonia, Slovakia, and Spain. And Slovakia is already revoking the certificates of these keys. The access to the datasets from electronic ID documents was difficult to come by. However, other domains are quite easy to survey, such as PGP mail encryption. We downloaded the keys from PGP key servers and were able to find hundreds of factorable keys. These chips are also used in authentication tokens, and these are not always made just by Infineon, but can be sold under other labels. If these tokens use RSA for challenge response authentication, they may be affected. Another problematic domain for this problem is software signing, both in the signing of software releases and for commit signing. Due to the nature of source control systems, it's difficult to change history of your commits and re-sign them. Many other applications take advantage of the programmable smart cards, such as on the Java card platform, and these may sometimes use even shorter keys due to the performance reasons. Thanks to the powerful fingerprinting method, which runs extremely fast, we were able to survey a very large data set of public RSA keys used for TLS. These were coming from scans by Census.io and from certificate transparency. Luckily, only a very small number of keys were affected. These were all somehow tied to supervisory and control systems. Moving on to mitigations, you should probably test your public keys for the fingerprint, and you can find the online tool and the open source code on our website, also displayed in the upper right corner. If you find your keys to be vulnerable, you should revoke the certificates, but remember that this comes with disadvantages, as other following mitigations will come to. In this case, the services relying on these certificates will become unavailable. You can still use these affected chips if you change the algorithm in your infrastructure. For example, many of these chips support elliptic curve cryptography, and both Estonia and Slovakia are switching to elliptic curves in their EIDs. However, this means that you must update all the infrastructure to use this new algorithm. If you need to stick with RSA, you should generate new secure keys. This will, however, require a firmware update, which is not available for all devices, which might mean that you will have to replace your device, which can be costly. Alternatively, you can import a securely generated RSA key pair into your smart card. We are not aware of any vulnerability connected with the use of secure keys on these chips. But remember that this requires trusted environment for both the key generation and the import. If none of these solutions are available, then you may want to temporarily switch to less affected key lengths, such as the example from the slide with complexity. But remember that many of these keys still have significantly reduced security level, and in case that our attack improves, they may become factorable soon. If you are dealing with keys which are generated outside of your domain, you may want to test the keys for vulnerabilities, for example, using our open source code, and then employ additional risk management when you find such keys. I will now briefly discuss the timeline of finding this attack. By the end of January, we recovered the structure of the primes and developed a proof of concept attack. By February 1st, we notified the manufacturer and gave them 8 months of responsible disclosure time, in which we did not release the details of the attack. The first public information about this attack was due to Microsoft releasing the patches for TPMs. This was about 1 week before we made our public disclosure, in which we gave the fingerprint testing method, but we did not release the factorization attack yet. This did not stop cryptographers Tanja Lange and Dan Bernstein, who announced a faster version of the attack in the same week, and they developed it working with just the public information. In the meantime, the community was busy looking for the vulnerable keys, and they were able to locate them in devices manufactured as soon as in 2007 and possibly earlier. On October 30th, 2 weeks after the public disclosure, ACM published the full paper. So what can we learn from this? Some optimizations in cryptography may weaken the security of the system. Moreover, the design and implementation of this key generation method was not made public, which delayed the discovery of the flaw. This was approximately 10 years before it was found by us. In the meantime, possibly hundreds of millions of such devices were manufactured and sold, which increased the impacts across all domains. Even though this library was checked and certified by independent expert labs, the vulnerability was not found, which is hinting at some issue with the certification process. We believe that the developers should be encouraged to publish their documentation and implementations, at least for cryptographic algorithms. Such vulnerabilities could be prevented in the future, for example, by avoiding a single point of failure. There is a lot to be learned from a very well documented area of secure multi-party computations. There have been several talks here as well. However, these solutions are not always drop-in replacements and require extra work. One specific area which comes close is collaborative RSA key generation and use, which is also applied in practice. It's not just an academic issue, and it's being successfully used in Baltic countries for their smart ID system, in which the mobile phones and the servers collaborate to generate RSA keys and RSA signatures, and the verification of such signature is done with classic RSA. Before I move on to questions, I would like to say that 4 of our team members are here today, except for Vasek, who couldn't make it. So if you have any questions for us during this day, we will be happy to answer them. And also, we have the representatives from Infineon here today in the 5th row. So you can as well discuss with them. They will be happy to answer your questions. So that concludes my talk. Thank you for your attention, and we can move on to questions.
Hi, Jean-Pierre Seifert. So great talk. Thank you very much for doing this great work. So obviously, if you go to this slide, of the structure of the prime, it's obviously, I would say somehow a kleptographic attack according to Matus' talk, because it's clear whoever did the structure of the prime should have seen, right, that it's far from uniform, because not the general programmer comes to that point. Okay, I do the prime in this way, because only somebody who has enough knowledge, in number theory will come with this and see that it's far from uniform. I can tell you also how it happened. So I would wonder, what was the real answer from Infineon when you notified them? From Wieland Fischer especially.
Well, they acknowledged the issue, and they immediately started to work on the mitigations. I would just like to note about your remark earlier that, of course, this is not uniformly distributed. However, if we go back to the paper which we published last year, you would see that almost no implementation is able to make this uniform distribution.
Yeah, sure. But, their distribution looks quite different, right, than the others, right?
Well, I believe it was not common before to compare the distributions as we did. So maybe this wasn't so obvious at first.
I would say it's quite obvious, that you don't do it this way. Because they are also, I read it also in your paper, they also, other from these two Gemblus guys, right? There's another structure how to generate the primes, which is far away from this, right? So for my being, it's quite obvious, why it was done this way.
Well, it's for the efficiency improvements. I can't really speak for Infineon. You may discuss this offline with the guys.
Now,
but
I would suggest that you look into, the papers from Moti Young, and then you will recognize why it was this done. I can give you
sorry,
also
which paper was that?
from Moti Young on all his kleptographic pieces, right? Kleptographic
Okay,
attack.
so you
I
are saying about the tutorial, which was on
Well,
Tuesday.
there was tutorial, and there were also Moti has papers, why we are dealing with such pieces there. I can give you also some points, from patents from Infineon, how it happened. At some point in time, it was changed, obviously. Let's discuss later. Okay. Thank you very much for this great talk.
Thank you.
Hello. I would like to add one point to the mitigations that you have. The common understanding is that Microsoft patched this vulnerability with the update in the Matus update. If you actually go and read the advisory, then what they have done is that they added a detection tool or a detection option for the vulnerable TPMs, and they pulled the key generation off from the TPMs. Actually, everybody who is working on corporate security should go reread the Microsoft advisory 3 times at least, and to understand if they actually need to apply patches to the TPMs themselves. Microsoft hasn't patched per TPM because they can't, it is firmware. What they did was that they took the key generation off and added detection tool to the operating system.
Okay, thank you for clarifying. As I understand it, it is possible to patch the firmware, but if it's as you say, then yeah, probably Microsoft.
Yeah, this is Joseph Kohn with Infineon. I'm actually responsible for our TPM business and like to add a little bit here. You're totally right. It's not Microsoft patching the TPMs. The TPM firmware updates are being available by the PC OEMs. This is an update that goes into the security chip, and the BIOS plays a role. Is it a TPM 1.2, TPM 2.0? Is it a legacy BIOS or a UEFI BIOS? So that's why the PC OEM, the maker of the PC, actually really controls the process. And Microsoft, as the operating system, is kind of just the guest on top of it. Microsoft introduced some patches handling and the recovery of BitLocker, for example, and other security features they take in place. And this, by the way, is the reason why it's really, and I would like to thank you guys from the university for the period of responsible disclosure of 6 months. It really took this time, and we immediately started working with coming up with new firmware versions, updating the BIOSes, providing tools to bring the firmware updates into the TPMs, validate this. This is really a complex system topic, and it took the 6 months. And again, thank you very much for giving the overall ecosystem the time to do that.
Thank you for the clarification. I believe it's very important to give the manufacturers time to fix these vulnerabilities, as we did with the 8 months of responsible disclosure.